Look up at the night sky on a clear evening, far from the glow of any city, and you are seeing light that has traveled for thousands, sometimes millions of years to reach you. But that light, ancient as it seems, is young compared to the story we are about to follow. Beyond the stars, beyond the most distant galaxies our telescopes can gather, there lies a moment so early that ordinary language begins to fail us. It is a moment measured not in years, not in seconds, but in fractions of a second so small that writing them out fully would fill a line with zeros. This is the domain of cosmic inflation, an idea that attempts to describe what happened in the very first instant of existence. The proposal is simple to state and difficult to grasp. In its earliest moment, the universe did not expand gently. It stretched at a rate that defies intuition, doubling in size again and again in a span of time shorter than anything we can meaningfully imagine. In that brief episode, the seeds of every galaxy, every star, and every atom were planted. What began as a smooth and featureless patch became the vast, structured cosmos we inhabit today. This is not idle speculation. It emerged from real problems that troubled physicists, gaps in the standard picture of the universe that no amount of careful measurement could close. Inflation was an attempt to answer questions that the older theory could not, and though it remains unproven in the strictest sense, it has left predictions we can test, faint patterns in the oldest light in existence. Over the coming exploration, we will trace how this idea took shape, what evidence supports it, and what mysteries it leaves unresolved. To understand why anyone would propose something as strange as cosmic inflation, we have to begin not with the theory itself, but with the moment it was invented to describe. And that means confronting a period of history so early that the familiar rules of the universe, the ones that govern stars and planets, and the light that moves between them, had not yet settled into place. When cosmologists speak of the beginning, they are careful with their words, because there is a boundary beyond which our current understanding simply stops. That boundary is not a wall in space. It is a wall in time, a moment after which physics can describe events with growing confidence, and before which every equation we possess breaks down into something meaningless. The universe, according to the evidence gathered over the past century, is expanding. Galaxies are drifting apart, and the space between them is stretching. This is one of the most secure findings in all of science, established through careful observation of how light from distant galaxies is shifted toward the red end of the spectrum, a stretching of the light itself that reveals the stretching of the space it travels through. If space is growing larger with each passing moment, then a simple thought experiment follows. Imagine running the process backward. If everything is moving apart now, then in the past everything was closer together. Push that reasoning far enough into the past, and the galaxies converge, the matter grows denser, the temperature climbs, and eventually the entire observable universe compresses into a region of unthinkable smallness and heat. This backward journey does not lead to a comfortable stopping point. Instead, it leads toward a state where the density becomes so extreme and the temperature so high that our two great theories of physics begin to contradict one another. On one side stands general relativity, the theory of gravity that describes how mass and energy bend the fabric of space and time. It works beautifully across enormous scales, guiding the motion of planets and the collapse of stars. On the other side stands quantum mechanics, the theory of the very small, which governs the behavior of particles and the strange probabilistic rules they obey. In ordinary circumstances, these two theories operate in separate arenas. Gravity dominates the large. Quantum effects dominate the small. But at the very beginning, when the entire universe was smaller than a single atom, both theories were forced to apply at once. And when we try to combine them there, The mathematics dissolves into infinities and nonsense. This is the reason cosmologists refer to a specific threshold, an interval of time after the beginning, before which we simply cannot see. It is often called the Planck era, named after the physicist whose work helped define the scales at which quantum gravity would become unavoidable. The numbers involved are so far outside daily experience that they resist any intuitive grasp. The duration of this era is a tiny sliver of a second, a value expressed by placing a decimal point and then a long string of zeros before the first meaningful digit. The temperature during this period would have been higher than anything that exists anywhere in the universe today, higher than the core of any star, higher than the debris of any explosion we can observe. Matter as we know it could not exist. The particles that make up your body, the protons and neutrons and electrons, had no stable form. Even the forces that govern them, the familiar distinctions between electromagnetism and the nuclear forces, may have been merged into a single unified interaction. Here, we must pause and be honest about what we do and do not know. The Planck era is not a place science has visited. It is a frontier we approach from the outside, reasoning our way toward it with the tools we have while acknowledging that those tools fail at the threshold. To describe what happened during that era with confidence, we would need a complete theory of quantum gravity, a way of uniting the physics of the large and the small into a single, coherent framework. Such a theory does not yet exist in finished form. There are candidates, ambitious mathematical structures that attempt to bridge the gap, but none has been confirmed by observation. So, when we speak of the earliest instant, we are speaking of a region where our best speculation is guided by physics but not yet secured by it. What we can say is that the conditions were unlike anything in the present cosmos. Consider the density. Today, if you were to spread all the matter in the observable universe evenly through space, you would find it astonishingly sparse, a few atoms scattered through each cubic meter of emptiness on average. In the earliest moment, that same matter, along with all its energy, was packed into a volume smaller than the period at the end of a sentence. Every galaxy that would ever form, every particle that would ever exist, occupied a space you could not see without a microscope. The energy concentrated in that tiny region was immense, and it is the behavior of that concentrated energy that sets the stage for everything to come. There is a temptation, when facing something this extreme, to imagine it as an explosion, a great burst of matter flung outward into a surrounding void. This picture is deeply misleading, and correcting it is essential to understanding what actually happened. The beginning was not an explosion within space, a firecracker going off in an empty room. It was an expansion of space itself. There was no room for it to explode into, because space was not yet a stage on which events unfolded. Space was part of the event. When we say the universe was small, we do not mean that it was a small object sitting somewhere. We mean that space itself, the very dimension in which distance is measured, was compressed. As the universe expanded, it did not spread into a pre-existing emptiness. It generated the emptiness as it grew. This distinction changes the way we must think about the earliest moment. Ask where the beginning happened, and the honest answer is that it happened everywhere, because every point in the present universe traces back to that same origin. The most distant galaxy and the ground beneath your feet share a common ancestry in that compressed state. There was no center, no special location from which everything emanated. The expansion was not outward from a point, but a uniform stretching of every distance at once. Now, with this foundation in place, we can begin to appreciate why the standard picture, powerful as it was, left cosmologists uneasy. The theory that grew out of this backward reasoning, the account of a hot, dense beginning, followed by expansion and cooling, achieved remarkable successes. It predicted the existence of a faint background of radiation left over from the early universe, radiation that was later discovered exactly as expected. It explained the relative amounts of the lightest chemical elements, the hydrogen and helium that were forged in the first minutes of cosmic history, and those predictions matched observation with impressive precision. By any reasonable measure, the framework worked, and yet it carried within it a set of assumptions that no one could justify. The theory could describe how the universe evolved once it was already hot and dense and expanding, but it could not explain why the universe began in the particular condition it did. It took the initial state as a given, a starting point to be assumed rather than understood. When physicists examined that assumed starting point closely, they found it strange in ways that were difficult to ignore. The universe appeared to have begun in a condition that was, from a certain point of view, extraordinarily improbable. It was too smooth in some respects and too precisely balanced in others. These were not errors in the theory. The mathematics functioned correctly. But the theory required initial conditions so finely arranged that their existence seemed to demand an explanation of its own. To grasp what troubled them, we can think of it this way. Suppose you walked into a room and found 1,000 pencils all standing perfectly balanced on their sharpened tips. Nothing in the laws of physics forbids such an arrangement. Each pencil, considered alone, could in principle stand on its point if placed with impossible precision. But finding all of them standing that way would compel you to ask what process had arranged them so carefully. You would not be satisfied with the answer that they simply began that way. You would want to know the mechanism. The early universe presented cosmologists with a similar unease. Its initial state was not impossible, but it was so special, so delicately tuned, that treating it as a mere assumption felt like avoiding the deeper question. This unease was not vague dissatisfaction. It crystallized into specific, well-defined problems that could be stated clearly and confronted directly. Each pointed to a different aspect of the universe that the standard theory described accurately but could not explain. And it was in the effort to solve these problems, to find a mechanism that would produce the finely tuned beginning naturally rather than assuming it, that the idea of inflation was born. Before we can follow that discovery, we need to examine the puzzles themselves, the concrete features of the cosmos that seemed too perfect to be accidental. The first and most striking of them concerns something you might expect to be simple. Why the universe, when we look in opposite directions across the sky, appears so remarkably, so suspiciously the same. The puzzle begins with a measurement, and the measurement concerns temperature. Scattered throughout the universe, filling every direction we look, is a faint glow of radiation. It is not visible to the eye because it lies in the microwave portion of the spectrum, but our instruments detect it easily. This radiation is the oldest light in existence, released when the universe was still young, and it carries information about conditions as they were long before any star had formed. We will return to this ancient glow in detail later, because it is central to the entire story. For now, what matters is a single fact about it. When we measure its temperature in one direction, and then turn our instruments to measure it in the opposite direction, across the entire width of the observable sky, the two temperatures agree. They agree not roughly, not approximately, but to a precision of a few parts in 100,000. Wherever we look, this radiation carries almost exactly the same temperature. At first glance, this sameness might seem unremarkable, even expected. Surely, a universe that began in a hot, dense state would cool evenly, arriving at the same temperature everywhere. But when cosmologists thought carefully about how temperatures become equal, they realized that this uniformity was not something the standard theory could explain. It was, in fact, deeply puzzling. And the reason involves one of the most fundamental limits in all of physics: the speed of light and the way it restricts how information and influence can travel through the universe. Consider how two objects come to share the same temperature in everyday experience. Place a hot cup of coffee on a cold table, and over time the coffee cools while the table warms slightly beneath it. Heat flows from the warmer object to the cooler one until they reach a balance. This process requires contact, or at least some form of communication, a way for energy to pass between them. Nothing can equalize its temperature with something it has never interacted with. If two objects have never exchanged energy, never sent any signal or influence to one another, there is no reason for them to match. They would each settle at whatever temperature their own history produced, and those temperatures could be wildly different. Now apply this reasoning to the universe. The radiation we measure in one direction has been traveling toward us for nearly the entire age of the cosmos. The radiation we measure in the opposite direction has likewise been traveling toward us for nearly the entire age of the cosmos, but from the other side. These two regions, the one on our left and the one on our right, are separated by an enormous distance. The light from each has only just reached us now. This means that light from one of those regions has never had time to reach the other. The two regions have never been in contact. No signal, no influence, no exchange of energy of any kind could have passed between them, because to do so would require traveling faster than light, and nothing does that. In the language of cosmology, these regions lie outside each other's horizon. They are causally disconnected, sealed off from one another by the finite speed at which influence can travel, and the finite time the universe has existed. Here, then, is the problem stated plainly. Two regions of the sky that have never been able to communicate, that have never shared any physical contact, nevertheless display the same temperature to extraordinary precision. How did they come to agree? If they never exchanged energy, what smoothed them to the same value? The standard theory offered no answer. It could describe the uniformity, but it could not produce it. The uniformity had to be inserted by hand, assumed as part of the initial condition, precisely the kind of unexplained fine-tuning that made cosmologists uncomfortable. This is called the horizon problem, and it was one of the sharpest thorns in the older picture of the universe. To feel the weight of it, imagine a different scenario. Suppose you sent 1,000 people to 1,000 isolated rooms, each with a thermostat, and told them nothing about what temperature to choose. You returned later to find that every single room had been set to exactly the same temperature, down to a fraction of a degree, even though none of the occupants had spoken to one another or coordinated in any way. You would not accept coincidence as an explanation. You would suspect that some hidden connection linked them, some shared influence you had overlooked. The horizon problem placed cosmologists in exactly this position. The uniformity of the ancient radiation demanded a hidden connection, a mechanism that had somehow allowed distant regions to reach agreement despite their apparent isolation. This was not the only such puzzle. A second problem concerned the overall shape, or geometry, of the universe. This may sound abstract, but it has a precise meaning. According to general relativity, the presence of matter and energy curves the fabric of space. Depending on how much matter and energy the universe contains, its overall geometry could take one of several forms. If the density were high enough, space would curve back on itself, closing like the surface of a sphere, so that a straight line traveled far enough would eventually return to its starting point. If the density were low, space would curve the other way, opening outward like the surface of a saddle, stretching endlessly with lines that diverge. And balanced precisely between these possibilities lies a third option, a flat geometry, in which space obeys the familiar rules we learned as children, where parallel lines never meet and the angles of a triangle sum to a predictable total. When cosmologists measured the geometry of our universe, they found it to be flat, or so close to flat that no deviation could be detected. This might seem like a pleasant simplicity, but on reflection it presented another puzzle. The flat case is a knife's edge, a perfect balance between the closed and open possibilities. And the mathematics revealed something troubling about that balance. Any tiny departure from perfect flatness in the early universe would have grown rapidly as the cosmos expanded. If the universe had started even slightly curved, that curvature would have amplified over time, becoming enormously more pronounced as the ages passed. For the universe to appear flat today, after billions of years of expansion during which any imbalance would have been magnified, it must have begun almost unimaginably close to perfect flatness at the outset. This is the flatness problem, and it echoes the discomfort of the horizon problem. Nothing in the standard theory forbade a flat universe, but producing one required the initial density to be tuned to a value so precise that it strained belief. The universe had to begin balanced on that knife's edge with breathtaking accuracy, and the standard theory could only assume this balance, never explain it. Once again, cosmologists found themselves facing a beginning that worked perfectly in the equations, yet demanded a mechanism to justify its own precision. Return to the image of the balanced pencils. A flat universe was like a pencil that had somehow stood on its tip, not for an instant, but across the entire history of the cosmos, refusing to fall even as every physical tendency should have toppled it long ago. There was a third puzzle, subtler than the others but pointing in the same direction. Certain theories of particle physics predicted that the extreme conditions of the early universe should have produced exotic, heavy particles in great abundance. Among these were objects called magnetic monopoles, hypothetical particles carrying a single magnetic charge, unlike ordinary magnets which always possess both a north and a south pole. If these theories were correct, the early universe should have manufactured monopoles in such quantities that they would be common throughout the cosmos today. Yet, we have never found a single confirmed example. They are, as far as observation can tell, entirely absent. Something must have happened to reduce their number to essentially nothing, to dilute whatever the early universe produced until it vanished from view. The standard theory offered no such mechanism. Taken together, these three puzzles shared a common character. In each case, the universe displayed a property that was not impossible, but was extraordinarily special. Uniform temperature across regions that could not have communicated. A geometry balanced on the finest of edges. An absence of particles that the physics of the early cosmos seemed obligated to produce. And in each case, the standard theory could accommodate the observation only by assuming a finely tuned initial condition, a beginning arranged with a precision that cried out for explanation. The equations were not wrong. They simply pushed the mystery back to the starting point and left it there, unexamined. For a time, some physicists were willing to accept this. Perhaps the universe simply began that way, they reasoned, and asking why was a question beyond the reach of science. But others found this unsatisfying. They believed that a special beginning was not an answer, but a question in disguise, and that a deeper theory ought to explain how such a beginning could arise naturally from more ordinary conditions. What was needed was a mechanism, some physical process operating in the earliest moments that would take a generic, unremarkable starting point and transform it into the smooth, flat, monopole-free universe we observe. If such a mechanism could be found, it would dissolve all three puzzles at once, replacing a trio of unexplained coincidences with a single physical process. The search for that mechanism is where our story turns next. It did not begin with someone setting out to solve the horizon problem or the flatness problem directly. Instead, it emerged, as many discoveries do, from a scientist working on something else entirely, following a chain of reasoning that led, almost by accident, to an idea capable of reshaping the entire picture. The insight, when it came, would suggest that the universe passed through a phase of expansion so rapid, so violently fast, that it defied every expectation of how a cosmos should behave. What could possibly drive space itself to stretch at such a rate? And how could a single idea resolve so many separate puzzles at once? The answer took shape at the beginning of the 1980s, in the mind of a young physicist named Alan Guth. He was not, at the time, a cosmologist by training. He was a particle physicist, someone whose work concerned the behavior of the smallest constituents of matter and the forces that bind them. This detail matters, because the idea of inflation did not arrive through the front door of cosmology, through someone deliberately attacking the horizon and flatness problems. It arrived sideways, through the work of a researcher wrestling with a question in particle physics that seemed, at first, to have nothing to do with the shape of the universe or the uniformity of its temperature. Guth had been thinking about those exotic particles mentioned earlier, the magnetic monopoles. The theories he studied predicted that these heavy objects should have formed in great numbers in the early universe, and their apparent absence was a genuine problem. In pursuing this question, he found himself examining what happens to certain kinds of energy fields when the universe cools from its initial extreme temperature. And it was here, in the mathematics of cooling fields, that he encountered something unexpected. Under particular conditions, the equations suggested that a region of the early universe could become trapped in a peculiar state, one where empty space itself carried a large amount of energy. And when he worked through the consequences of that trapped energy, he found that it would drive the universe to expand not gradually, but explosively, at a rate that accelerated with each passing instant. To understand why this was so surprising, we need to consider how gravity normally behaves and why it makes ordinary matter resist rapid expansion. Gravity, in our everyday understanding, pulls things together. The Earth holds us to its surface. The Sun holds the planets in their orbits. Across the cosmos, gravity draws matter into clumps, gathering gas into stars and stars into galaxies. It is an attractive force, always working to pull things closer. In a universe filled with ordinary matter, this attractive pull acts as a brake on expansion. As the universe expands, gravity fights against it, slowing the growth, tugging everything back toward togetherness. Left to matter alone, expansion should decelerate over time, like a ball thrown upward that gradually loses speed as gravity draws it back down. But general relativity contains a subtlety that most everyday intuition misses. In Einstein's theory, gravity does not respond only to mass. It responds to energy in all its forms, and crucially, it responds to pressure as well. This is a genuine departure from the older Newtonian picture of gravity, and it opens a door to strange possibilities. Ordinary pressure, the kind that pushes outward, actually contributes to gravitational attraction in Einstein's framework, adding to the pull rather than opposing it. But there exists, in principle, a different kind of pressure, a negative pressure, a tension that pulls inward rather than pushing outward. And when the mathematics of general relativity is applied to a substance with sufficiently strong negative pressure, the result inverts everything we expect. Gravity, in that circumstance, does not pull, it pushes. It becomes repulsive, driving space to expand rather than contract. This is the heart of the mechanism. If a region of the early universe could be filled with a form of energy that carried strong negative pressure, then gravity itself would work in reverse there, propelling the region to expand at an ever-increasing rate. The trapped energy and empty space that Guth had stumbled upon in his equations behaved in exactly this way. It possessed negative pressure. And so, rather than slowing the expansion as ordinary matter would, it accelerated it, doubling the size of the region, then doubling it again and again, each doubling taking the same tiny interval of time as the one before. This is the defining signature of inflation. Not steady growth, not even rapid growth, but exponential growth. A repeated doubling that multiplies distances by staggering factors in almost no time at all. The word exponential deserves careful attention because it describes a kind of increase that human intuition consistently underestimates. Consider a familiar illustration. Imagine a single grain of rice placed on the first square of a chessboard, then 2 grains on the second square, 4 on the third, doubling with each square across all 64. By the final square, the number of grains would exceed all the rice ever grown in human history, an amount so vast it could bury entire nations. And that is only 64 doublings. During inflation, the universe is thought to have undergone at least 60 doublings, possibly far more, in a span of time so short it defies comprehension. Each doubling took a tiny fraction of a second, and the whole episode was over almost as soon as it began. Yet in that flicker, a region far smaller than a single proton was stretched to a size larger than the entire observable universe today. The scale of the stretching is not something the mind can truly hold. It can only be pointed to and acknowledged. Now we can see why this idea, born in the study of particle physics, turned out to solve the puzzles of cosmology. Consider first the horizon problem, the mystery of why distant regions share the same temperature despite never having been in contact. Inflation offers a resolution that is almost elegant in its simplicity. Before the rapid expansion began, the region that would become our observable universe was not vast. It was minuscule, small enough that every part of it was in close contact with every other part. In that tiny initial patch, energy could flow freely, temperatures could equalize, and the whole region could settle into a uniform, balanced state, exactly the way a small cup of coffee reaches a single temperature throughout. The regions were in contact. They did communicate. They did exchange energy and reach agreement. Then inflation took hold, and that tiny uniform patch was stretched to enormous size in an instant. The regions that had been neighbors, close enough to share their warmth, were flung apart to opposite ends of the observable sky. By the time we measure them today, they appear impossibly distant, separated by gulfs that light could never have crossed in the age of the universe. They seem to have no shared history, no possible means of communication. But that appearance is an illusion created by the expansion itself. They did share a history. They were once in contact. Inflation carried them apart after they had already reached agreement, preserving the uniformity they had established while separating them beyond any hope of later communication. The sameness we observe is not a coincidence requiring fine-tuning. It is the fossil record of a moment when everything was small and connected. The same idea resolves the flatness problem with equal grace. Recall that the universe appears geometrically flat, balanced on a knife's edge between curving closed and curving open, and that this balance seemed to require impossible precision in the initial conditions. Inflation dissolves the difficulty through the sheer magnitude of the stretching. Picture the surface of a balloon that is only partly inflated. Its surface is noticeably curved, bending back on itself in every direction. Now imagine inflating that balloon to the size of a planet. If you stood on its surface, it would appear perfectly flat to you, because the curvature has been stretched so thin, spread across such an enormous area, that no local measurement could detect it. Inflation does the same thing to the geometry of the universe. Whatever curvature the cosmos may have possessed at the outset, the extreme stretching flattened it, spreading any bend across a region so vast that the portion we can observe appears flat regardless of how it began. The knife's edge is no longer a mystery, because inflation drives any starting geometry toward flatness automatically. And the third puzzle, the missing monopoles, yields to the same logic. If those exotic particles were produced before or during the earliest moments, inflation would have diluted them beyond recognition. The rapid expansion increased the volume of space by such a colossal factor that whatever density of monopoles existed beforehand would have been spread across an incomprehensibly larger region. Imagine a handful of particles scattered through a tiny volume, and then that volume expanding to the size of the observable universe. The particles, once crowded together, would find themselves separated by cosmic distances, so rare that the entire observable universe might contain only one or two or none at all. Inflation does not destroy the monopoles. It simply spreads them so thin that the chance of encountering one becomes vanishingly small. Their apparent absence is explained not by preventing their creation, but by diluting them into invisibility. This was the remarkable power of the idea. A single mechanism, a brief episode of accelerated expansion driven by energy with negative pressure, resolved three separate puzzles that had troubled cosmologists for years. It did not require three different assumptions, three different fine-tunings. One process accounted for all of them at once. This is the kind of unification that scientists find deeply persuasive, because it suggests that the idea is not an arbitrary patch but a reflection of something true about how the universe actually behaved. When one clean concept explains several unrelated observations, it earns a kind of credibility that no single explanation could provide on its own. Yet for all its explanatory reach, Guth's original formulation contained a serious flaw, and he recognized it himself. The problem lay in how inflation was supposed to end. For the theory to work, the universe could not remain in its rapidly expanding state forever. At some point, the accelerated expansion had to stop, the trapped energy had to be released, and the universe had to transition into the ordinary, hot, matter-filled state that would eventually cool into the cosmos we know. In Guth's initial version, this transition happened through a process that would have left the universe wildly uneven, broken into isolated pockets rather than the smooth, continuous space we observe. The mechanism that started inflation worked beautifully. The mechanism that ended it did not. The theory, in its first form, could not gracefully bring itself to a close. This was not a fatal blow, but a challenge, an invitation for other physicists to refine the idea. Within a short time, researchers proposed improved versions that solved the ending problem by allowing inflation to conclude smoothly and uniformly across all of space at once. These refinements preserved everything that made the original idea attractive, while removing its central defect. But they also raised a deeper question, one that had been present from the beginning, yet demanded a clearer answer. What exactly was this energy that filled empty space and drove the expansion? What was the source of the negative pressure? To speak of trapped energy in the vacuum is to name a behavior without identifying its cause. If inflation truly happened, something had to be doing the inflating. Some physical entity whose properties would determine everything about how the rapid expansion unfolded and how it eventually came to an end. That entity, still unseen and still unconfirmed, is where our inquiry must turn next. The entity physicists propose to drive inflation is called a field, and the concept of a field is worth pausing over because it lies at the foundation of how modern physics describes reality. A field, in the language of physics, is a quantity that has a value at every point in space. This may sound abstract, but you have encountered fields your entire life without naming them. The temperature in a room is a field, because at every location there is some temperature, and those values can vary smoothly from the warm air near a heater to the cooler air by a window. A more instructive example is the magnetic field surrounding a magnet. You cannot see it directly, but scatter iron filings on a sheet of paper held above the magnet, and they arrange themselves into curving lines, tracing the invisible structure that fills the space around the object. The field was always there, occupying the seemingly empty region, exerting influence, waiting only for something sensitive to reveal it. Modern physics holds that empty space is not truly empty at all. It is filled with fields, an overlapping collection of them, each extending throughout the cosmos, each capable of carrying energy and exerting influence. The particles we think of as the fundamental building blocks of matter, the electrons and quarks and all the rest, are understood in this framework not as tiny solid objects, but as localized disturbances in their respective fields, ripples in an underlying medium that pervades all of space. What we call a particle is, in this view, a concentrated vibration in a field that is otherwise spread everywhere. This is one of the deepest and most well-tested ideas in all of science, confirmed repeatedly in experiments that probe the behavior of matter at the smallest scales. For inflation to work, physicists proposed that there existed, in the earliest moments of the universe, a particular field whose behavior would drive the rapid expansion. Because its purpose was to produce inflation, they gave it a name derived from that role, calling it the inflaton, a field whose defining feature was its capacity to fill space with energy and generate the negative pressure that inverts gravity. The inflaton has never been directly observed. It remains a proposed entity, a piece of physics invoked to explain the behavior the theory requires. But its properties can be described with mathematical precision, and understanding those properties is the key to understanding how inflation began, persisted, and ended. The crucial feature of the inflaton is the relationship between its value and the energy it carries. To picture this, physicists use an image that appears throughout their reasoning about such fields, the image of a ball resting on a curved landscape. Imagine a surface shaped like a valley, or like the inside of a bowl, and imagine a ball placed somewhere on that surface. The height of the ball on the landscape represents the amount of energy the field carries. When the ball sits high on the slope, the field carries a great deal of energy. When the ball rolls down into the low point at the bottom, the field carries little or no energy. The shape of this landscape, the particular way it rises and falls, is what physicists call the potential, and it governs how the field behaves over time, much as the shape of a real hillside governs how a real ball would roll across it. The behavior of a ball on such a landscape follows a logic we all understand from experience. A ball placed on a steep slope rolls downhill quickly, gathering speed as it descends. A ball placed on a gentle, nearly level slope rolls slowly, creeping downhill at a leisurely pace. And a ball resting in the low point at the bottom of the valley stays there, having reached the lowest energy it can hold. The inflaton, according to the theory, behaves in just this way, its value sliding across the landscape of possible energies as the field seeks its lowest state. And the pace of that slide determines everything about how inflation unfolds. Here is where the shape of the landscape becomes decisive. For inflation to work, for the rapid expansion to persist long enough to smooth the universe and flatten its geometry, the inflaton must spend a substantial stretch of time carrying a large, nearly constant amount of energy. This requires a landscape with a particular form, a broad region that is high but very nearly flat, an extended plateau across which the ball rolls only slowly before eventually reaching the steeper descent that leads down to the valley floor. While the field lingers on this high plateau, changing its value only gradually, empty space is filled with a large and steady energy, and that energy carries the negative pressure that drives the exponential expansion. The universe inflates, doubling and redoubling, for as long as the field remains on the plateau, taking its slow journey across the nearly level terrain. This slow rolling across a flat plateau is the mechanism that sustains inflation, and it resolves the difficulty that troubled Guth's original version of the theory. In that first formulation, the field had been trapped in a state from which it could escape only through an abrupt and uneven process, leaving the universe broken into disconnected pockets. The refined picture replaced that abrupt escape with a smooth, gradual descent. The field does not remain trapped and then break free chaotically. It rolls slowly and continuously down a gentle slope, maintaining the inflationary energy throughout its long journey across the plateau. And then, when it reaches the region where the landscape steepens, it accelerates downward toward the valley floor, and inflation comes to an end. The transition is smooth, uniform, and complete across all of space, precisely the graceful ending the original theory had lacked. The amount of expansion that occurs depends on how long the field takes to cross the plateau, which in turn depends on the exact shape of the landscape. A broader, flatter plateau means a longer journey, more time spent inflating, and a greater total expansion. This is why the details of the potential matter so much. They determine how many times the universe doubled in size, and therefore how thoroughly the horizon and flatness problems were solved. For inflation to accomplish what the theory requires, the landscape must be shaped so that the field crosses the plateau slowly enough to allow at least 60 doublings, and perhaps many more. The precise form of that landscape is not known, because we have not identified the inflaton or measured its properties directly. Physicists have proposed many possible shapes, many candidate potentials, each producing slightly different predictions, and distinguishing among them is one of the central tasks of modern cosmology. There is a profound strangeness in the idea that empty space could carry energy at all, and it deserves to be confronted directly rather than passed over. Our ordinary intuition tells us that a vacuum, a region emptied of all matter, should contain nothing, and therefore should carry no energy. But the field picture overturns this intuition completely. According to the theory, the inflaton field permeates all of space, and even where there are no particles, no matter of any kind, the field still has a value, and that value corresponds to an energy. Space that appears utterly empty can be filled with the energy of a field resting at some point on its landscape. During inflation, the entire observable universe was empty of ordinary matter in the usual sense, yet it was saturated with the energy of the inflaton field, and it was this energy of the vacuum itself, that drove the whole extraordinary process. This vacuum energy has a peculiar and essential property that ordinary matter lacks, and it explains the negative pressure at the center of the mechanism. When ordinary matter expands to fill a larger volume, it thins out. Spread a fixed amount of gas through a larger container, and its density drops because the same amount of material now occupies more space. But the energy of the inflaton field, while the field rests on its plateau, does not thin out as space expands. The field maintains its value everywhere, and so every region of space, no matter how much it has grown, carries the same energy density as before. As the universe doubles in size, the total energy does not stay fixed and spread thinner. Instead, the newly created space is filled with the same energy density as the old, so the total energy grows along with the volume. Space expands, and the energy contained within it increases in proportion, drawn from the field that fills every point. This property, that the energy density remains constant even as space expands, is precisely what produces the relentless, self-sustaining character of inflation. Because the energy density does not dilute, the driving force behind the expansion does not weaken. The negative pressure remains as strong after each doubling as it was before, and so the next doubling proceeds at the same furious pace. Ordinary matter would have slowed the expansion, thinning and weakening its own gravitational influence as it spread. The inflaton field does the opposite. It maintains its full strength no matter how much the universe grows, driving expansion that feeds on itself, each doubling setting the stage for the next, until the field finally rolls off the plateau, and the whole process winds to a close. We should be careful here to distinguish what is firmly established from what remains hypothetical, because the two are woven together in this account, and honesty requires separating them. The concept of a field carrying energy throughout space is not speculative. It is the bedrock of modern physics, confirmed in countless experiments. The idea that certain fields can produce negative pressure and thereby drive accelerated expansion follows rigorously from general relativity, a theory tested to extraordinary precision. What remains hypothetical is the existence of the specific inflaton field itself, the particular entity proposed to have driven inflation in the early universe. We have not detected it. We do not know the shape of its landscape. We cannot yet say with certainty that it existed at all. The inflaton is a well-motivated proposal, grounded in principles we trust, but it has not been confirmed the way the electron or the ordinary fields of particle physics have been confirmed. This uncertainty is not a weakness to be hidden, but a feature of honest science at the frontier. Inflation is a framework, a family of related models, rather than a single finished theory with every detail nailed down. The core idea that a slowly rolling field drove a brief episode of exponential expansion is shared across all versions. But the specifics vary, and those specifics have consequences that can, in principle, be tested against observation. Different shapes for the inflaton's landscape predict slightly different patterns in the universe that resulted, and by measuring those patterns with ever greater precision, cosmologists hope to narrow down which version, if any, corresponds to what actually happened. The theory makes itself vulnerable to disproof, which is exactly what a scientific theory should do. There remains, however, a question that cuts even deeper, one that pushes against the boundary between what physics can currently explain and what still lies beyond it. We have described how inflation, once started, would proceed and eventually end. But we have not explained how the field came to be on its plateau in the first place, why the universe began with the inflaton, poised at high energy, ready to roll. And there is another puzzle, stranger still, that emerges when we consider the expansion itself. If inflation stretched space faster than light could travel across it, doubling distances in fractions of an instant, does this not violate the most fundamental limit in all of physics, the rule that nothing can move faster than light? How can space itself outrun the very speed that light establishes as the ceiling for all motion? The apparent contradiction dissolves once we understand exactly what the speed of light limit does and does not forbid, and the distinction turns out to be one of the most illuminating in all of physics. The rule, established by Einstein's special theory of relativity, is precise. It states that no object, no particle, no signal, no piece of information can travel through space faster than light. A spaceship cannot outrun a beam of light. A message cannot be sent from one place to another faster than light could carry it. Anything that moves through space from one location to another is bound by this ceiling. This limit has been tested exhaustively and never once found to fail. It is among the most secure principles we possess. But notice the careful phrasing. The limit governs motion through space. It concerns objects and signals traveling from one point to another within space. Inflation does not involve anything moving through space in this sense. Nothing races across the cosmos from one location to another. Instead, space itself expands. The distance between points grows, not because those points are moving through space, but because new space is, in effect, appearing between them. This is a fundamentally different kind of process, and the speed of light limit says nothing about it. There is no rule in physics that caps how quickly space itself can stretch. The ceiling applies to motion within space, not to the expansion of space itself, and this distinction, subtle as it sounds, is the entire resolution. To make this concrete, imagine two ants standing on the surface of a balloon, some distance apart. Neither ant moves, their feet remain planted exactly where they are on the rubber surface. Now begin inflating the balloon. As the rubber stretches, the two ants find themselves growing farther apart, even though neither has taken a single step. The distance between them increases, not because they are crawling across the surface, but because the surface between them is expanding. If you inflated the balloon rapidly enough, the ants could recede from one another at any rate you chose, faster and faster as the balloon grew, and yet neither ant would ever move relative to the rubber beneath its feet. The speed at which they separate has nothing to do with how fast they can crawl. It is determined entirely by how fast the surface stretches. The expansion of the universe works in just this way, with galaxies playing the role of the ants and space playing the role of the rubber. Galaxies are, for the most part, not moving through space in any dramatic sense. They sit more or less where they are, held in place by their local gravity. But the space between them expands, carrying them apart. And here we arrive at a consequence that surprises nearly everyone who first encounters it. Because the expansion of space adds up across distance, the farther apart two galaxies are, the faster the space between them stretches, and the more quickly they recede from one another. Beyond a certain distance, this recession exceeds the speed of light. There are galaxies in the universe today that are receding from us faster than light travels, not because they are moving through space at such speeds which would be forbidden, but because the vast expanse of space between us and them is expanding, and all that expansion, summed across the enormous distance, adds up to a recession faster than light. No law is broken, because nothing is moving through space at that rate. Space itself is simply growing. During inflation, this effect was magnified beyond all ordinary experience. The expansion was so rapid, the doubling so relentless, that even regions extremely close together were driven apart faster than light almost immediately. A patch of space, tiny at the outset, would find its opposite edges receding from one another at superluminal rates within the first instant of inflation, and the separation would only accelerate from there. Points that had been neighbors close enough to touch were swept beyond each other's reach in a fraction of a moment, carried apart by the stretching of the space between them. This is why inflation could take a region in intimate contact and fling its parts to opposite ends of the observable universe. The parts did not fly apart through space. The space between them exploded outward, and they rode along with it, planted in the rubber as it stretched. This picture illuminates a concept we touched on earlier, but can now understand more fully: the concept of a horizon. Because space can expand faster than light travels across it, there are limits to what we can ever see or influence. Light leaving a sufficiently distant galaxy today will never reach us, because the space between us is expanding faster than the light can cross it. The light struggles forward, but the distance it must cover grows faster than it can advance, like a swimmer trying to reach a shore that recedes faster than they can swim. Such galaxies lie beyond our horizon, forever beyond our sight, not because they are too faint, but because the geometry of the expanding universe places them permanently out of reach. The horizon is not a wall. It is a boundary defined by the race between light and the expansion of space, and beyond it lies a region we can never observe, no matter how patient we are or how powerful our instruments become. Understanding this helps clarify why the horizon problem was so severe and why inflation resolves it so cleanly. Regions on opposite sides of our sky lie beyond each other's horizons. Light from one could never have reached the other across the age of the universe because the expansion kept the distance between them growing, and yet they share the same temperature. The only way this makes sense is if they were once close enough to be within each other's horizons, close enough to exchange energy and reach agreement, before the expansion drove them apart. Inflation provides exactly this history. Before the rapid expansion, everything we now observe was packed into a region small enough that every part lay within every other part's horizon. Contact was possible. Agreement was reached. Then inflation stretched that region enormously, pushing its parts beyond one another's horizons, so that today they appear disconnected despite their common past. The horizon we observe is a consequence of the expansion, and inflation reshaped that horizon in a way that explains the uniformity we measure. There is a further subtlety worth drawing out, because it touches on how the character of the expansion has changed over cosmic history. During inflation, the expansion was accelerating, each doubling faster than intuition allows, driven by the constant energy density of the inflaton field. After inflation ended, the universe entered a long period in which the expansion continued, but gradually slowed, decelerating under the gravitational pull of the ordinary matter and radiation that now filled space. For billions of years, the expansion coasted, growing ever larger but at an ever gentler pace, as matter's attractive gravity applied its steady brake. This is the expansion that the backward reasoning of earlier cosmology had traced. The ordinary post-inflationary growth of a universe filled with matter and light. But the story took another turn, one discovered only at the close of the 20th century. Careful observations of distant exploding stars revealed that the expansion of the universe is not merely continuing, but has begun, in the relatively recent cosmic past, to accelerate once again. Something is driving space to expand at an increasing rate, echoing, in a much gentler form, the behavior that inflation displayed in the first instant. This present-day acceleration is attributed to a mysterious component called dark energy, an energy that appears to fill space and carry the same kind of negative pressure that drove inflation, though at a vastly lower intensity. The parallel is striking. In its first moments, the universe inflated furiously, driven by the energy of a field. Now, billions of years later, it accelerates again, driven by an energy we do not yet understand. Whether these two episodes of acceleration share a common cause, whether dark energy and the inflaton are related in some deep way, remains one of the great open questions of cosmology. We should be clear about what the analogy does and does not establish. The discovery of present-day acceleration does not prove that inflation occurred, and dark energy is not the same as the inflaton, at least not as far as anyone can currently demonstrate. But the fact that the universe is capable of accelerated expansion, that space really does contain forms of energy with negative pressure that drive it to stretch, lends a kind of plausibility to the inflationary idea. The mechanism inflation requires is not exotic in principle. The universe demonstrates, in the present epoch, that such mechanisms exist. Inflation asks us to accept that a similar but far more powerful mechanism operated in the beginning, and the observation of dark energy shows that the underlying physics is at least real, at least present in the cosmos we inhabit. Having established that space can expand faster than light without contradiction, that this expansion defines the horizons limiting what we can observe, and that the universe both inflated in its infancy and accelerates in its old age, we are prepared to confront the most remarkable claim that inflation makes. So far, we have treated inflation as a smoothing process, a mechanism that irons out irregularities, equalizes temperatures, and flattens geometry. And it does all of these things, but if inflation only smoothed the universe, if it produced nothing but perfect uniformity, then we would face a new problem. A perfectly smooth universe would contain no galaxies, no stars, no planets, no observers to wonder about any of it. For structure to form, for matter to gather into the cosmic web we observe, the early universe needed not only smoothness, but also tiny departures from smoothness, minuscule variations from which everything larger could grow. And here, inflation reveals its most extraordinary consequence. The very same process that smoothed the universe also, through the strange rules of quantum mechanics, planted within it the seeds from which all structure would eventually arise. How could a process of smoothing also be a process of seeding? And where did those seeds come from? The answer lies in the quantum world, in a principle so counterintuitive that it took physicists decades to accept, and it transforms our understanding of what empty space truly is. We spoke earlier of the vacuum, of empty space, as though it were a placid, featureless backdrop. But at the smallest scales, governed by the rules of quantum mechanics, the vacuum is nothing of the sort. It churns, it fluctuates, it is alive with restless activity that never ceases. This is not metaphor or loose speaking. It is a precise and experimentally verified feature of how reality works at its foundations, and it is the source of the seeds from which every galaxy grew. The principle responsible is called the uncertainty principle, one of the cornerstones of quantum mechanics. In its familiar form, it states that certain pairs of properties cannot both be known with perfect precision at the same time. The more precisely you pin down a particle's position, the less precisely its momentum can be determined, and the reverse holds as well. But the principle has a deeper consequence that reaches into the nature of empty space itself. It implies that a field cannot rest at a perfectly definite value with perfectly zero activity. There is always a residual jitter, an unavoidable trembling in the value of every field, even in the emptiest vacuum. If a field could sit perfectly still at a fixed value, that would represent a kind of precision the uncertainty principle forbids. And so, every field everywhere is always fluctuating, its value flickering up and down by tiny amounts in a ceaseless quantum dance. These fluctuations are ordinarily too small to notice. In everyday life, and even in most laboratory experiments, the quantum jitter of fields is so minuscule that it has no observable effect on anything larger than individual particles. The fluctuations appear and vanish almost instantly, tiny disturbances that flicker into existence, and then subside back into the background, too fleeting and too small to leave any lasting mark. On the scale of a human being, or a planet, or a star, these quantum tremblings average out to nothing, hidden beneath the smooth and stable reality we perceive. They are real, and their effects can be measured in delicate experiments designed to detect them, but they belong to the realm of the extraordinarily small. Now consider what happens when such fluctuations occur during inflation. The inflated field, like every field, was subject to these unavoidable quantum tremors. As it rolled slowly across its landscape, its value did not slide perfectly smoothly. It jittered, fluctuating up and down by tiny amounts from place to place, as the uncertainty principle demands. In one region, the field might be nudged slightly ahead in its roll, carrying slightly less energy. In a neighboring region, it might lag slightly behind, carrying slightly more. These variations were minuscule, the ordinary quantum jitter present in any field. Under normal circumstances, they would have flickered away to nothing, as they always do. But inflation was not a normal circumstance. Inflation was stretching space at an exponential rate, and this changed everything about the fate of those tiny fluctuations. Here is the crucial process, the mechanism by which the microscopic became the cosmic. Ordinarily, a quantum fluctuation appears and then vanishes almost immediately, existing for only the briefest instant before subsiding. But during inflation, the moment a fluctuation appeared, the relentless expansion seized it and stretched it. Before the fluctuation could flicker away, the expansion had enlarged it, pulling its tiny extent across a growing swath of space. And as the expansion continued, the fluctuation was stretched further still, pulled to a size so large that it could no longer subside. It became frozen, locked into the fabric of space, its variation preserved rather than erased. What began as a fleeting quantum tremor, smaller than any particle, was inflated to macroscopic size and imprinted permanently onto the expanding universe. The expansion did not merely smooth the large-scale universe, it simultaneously caught the smallest quantum fluctuations and blew them up into real, lasting variations spread across space. This is a genuinely startling idea, and its implications deserve to be stated plainly. The variations in density that would eventually grow into galaxies, into clusters of galaxies, into the entire vast architecture of the cosmos, did not originate from some large-scale process. They originated from quantum fluctuations, from the irreducible jitter of a field at the smallest imaginable scale, magnified by inflation into the seeds of all cosmic structure. Every galaxy, every star, every planet, and by extension every living thing, traces its ultimate origin to a quantum tremble in the early universe, a tiny random fluctuation stretched to enormous size by the expansion of space. The largest structures in existence grew from the smallest disturbances imaginable. The cosmic and the quantum, ordinarily separated by an immense gulf of scale, are joined at the beginning, the one giving birth to the other. We should follow the consequences carefully because they explain the universe we actually observe. Once inflation ended and the frozen fluctuations were imprinted on space, the universe contained tiny variations in density from place to place. Some regions held slightly more matter and energy than average. Others held slightly less. These differences were exceedingly small, variations of only a few parts in 100,000, but they were enough. Gravity, patient and relentless, went to work on them. In the regions that were slightly denser, gravity had a little more matter to pull on, and it drew in surrounding material, making those regions denser still. As they grew denser, their gravity strengthened, allowing them to attract even more matter, in a process that fed upon itself across hundreds of millions of years. The slightly under-dense regions, meanwhile, gave up their matter to the denser ones and grew emptier, eventually becoming the vast voids that separate the structures we see. Over cosmic time, this process transformed the nearly smooth early universe into the richly structured cosmos of today. The tiny seeds planted by inflation grew into the first stars and galaxies, which gathered into clusters, which arranged themselves along immense filaments stretching across the sky, with great empty voids between them. This large-scale arrangement, sometimes called the cosmic web, is the grandest structure in the universe, and its ultimate origin lies in those magnified quantum fluctuations. When astronomers map the distribution of galaxies across the sky and find them woven into this vast web of filaments and voids, they are looking at the grown-up descendants of quantum tremors from the first instant of time. The pattern we observe on the largest scales is the quantum jitter of the inflaton, enlarged and made concrete by billions of years of gravitational assembly. What makes this account scientifically powerful, rather than merely poetic, is that it makes precise predictions. Inflation does not simply assert that fluctuations existed. It predicts specific properties they should have, properties that follow from the mathematics of quantum fields being stretched by exponential expansion. One such prediction concerns how the fluctuations should be distributed across different scales. Because the inflationary expansion proceeded at a nearly constant rate, stretching fluctuations of all sizes in a similar manner, the resulting variations should be nearly the same strength across a wide range of scales, from the small to the very large. The fluctuations should be, in the technical language, nearly scale invariant, meaning that the universe should look statistically similar whether you examine it on smaller or larger scales, with only a slight and predictable tilt toward one end. This is a specific, testable claim, and it distinguishes inflation from alternative ideas that would produce different patterns. Inflation makes another prediction as well, one concerning the statistical character of the fluctuations. Because they arose from quantum processes, the fluctuations should be random in a particular way, following the same statistical distribution that governs many random processes in nature, the familiar bell-shaped curve that appears whenever many small independent effects combine. The variations should be distributed around the average in this characteristic pattern, without unusual features or preferred values. This, too, is testable. If the fluctuations we observe in the early universe matched this predicted statistical character, it would support the idea that they arose from quantum fluctuations during inflation. If they showed some markedly different pattern, it would count as evidence against the theory. These predictions are not vague. They are quantitative, specific, and vulnerable to disproof, which is exactly what gives inflation its scientific credibility. A theory that could explain anything would explain nothing, because no observation could ever contradict it. Inflation is not like that. It commits itself to particular claims about the pattern of primordial fluctuations, claims that could turn out to be wrong when confronted with observation. The theory sticks its neck out, and this raises the obvious question that must occupy us next. If inflation predicts a specific pattern of fluctuations imprinted on the early universe, can we find that pattern? Is there some way to look back at the universe as it was in its infancy and read the imprint that inflation should have left to check whether the predicted seeds are actually there? Remarkably, there is. The universe preserves a record of its early state, a faint signal that has traveled to us across almost the entire span of cosmic time, carrying within it the very pattern that inflation predicts. To read that record, we must turn to the oldest light in existence. That light surrounds us at this very moment, arriving from every direction in the sky, and it is the most important single piece of evidence in all of cosmology. To understand what it is and why it carries the imprint of the early universe, we need to follow the history of the cosmos forward from the end of inflation, through the long cooling that followed, to the moment when this light was set free. The story of that light is the story of how the universe became transparent, and it reveals the conditions of the early cosmos with a clarity that no other observation can match. When inflation ended, the universe was left hot, dense, and filled with a churning mixture of matter and radiation. For hundreds of thousands of years afterward, it remained too hot for atoms to form. The temperature was so high that electrons could not bind to nuclei. Whenever an electron tried to attach itself to a proton to form a hydrogen atom, a photon of radiation would immediately strike it and knock it loose again. The universe during this period was a plasma, a soup of free electrons and bare atomic nuclei all mixed together with an intense sea of radiation. And this plasma had a crucial property. It was opaque. Light could not travel freely through it. A photon moving through the sea of free electrons would travel only a short distance before colliding with one of them and scattering off in a new direction. The photons ricocheted endlessly among the electrons, unable to move in a straight line. unable to cross any significant distance without being deflected. The early universe, for all its heat and energy, was foggy, a glowing mist through which no light could pass cleanly. We know this kind of opacity from experience, even if we do not usually think of it in these terms. The interior of the sun is opaque for the same reason, a hot plasma in which light scatters endlessly rather than traveling freely. A dense fog scatters light in a similar way, which is why you cannot see clearly through it. The early universe was, in effect, glowing fog everywhere, filled with light that could not travel, endlessly scattering among the free electrons that filled all of space. Any observer, had one existed, would have seen only a uniform glow in every direction, with nothing visible beyond the nearest fraction of a distance, because the light carried no clear image, having been scattered too many times to preserve any information about where it came from. As the universe expanded, it cooled, and eventually a threshold was reached. Roughly a few 100,000 years after the beginning, the temperature dropped low enough that electrons could finally bind to nuclei and remain bound, without being immediately knocked free by radiation. Across the cosmos, electrons combined with protons to form stable, neutral atoms of hydrogen, and with the heavier nuclei to form helium. This event is called recombination, though the name is slightly misleading, since the electrons and nuclei were combining for the first time rather than recombining. The consequence of this event was profound. Once the free electrons were swept up into neutral atoms, they were no longer available to scatter light. The fog cleared. Suddenly, for the first time in cosmic history, light could travel freely, moving in straight lines across vast distances without being deflected. The universe became transparent. The radiation that had been trapped in the plasma, endlessly scattering, was released at this moment to travel freely through the newly transparent universe. And it has been traveling ever since for billions of years, across the entire span of cosmic history, until some tiny fraction of it reaches our instruments today. This is the oldest light in existence, the radiation released at the moment of recombination, when the universe first became transparent. It has been journeying toward us for almost the whole age of the cosmos, and it carries within it a picture of the universe as it was at that moment, the moment the fog cleared. We call it the cosmic microwave background, because the expansion of the universe has stretched its wavelength over the eons, shifting it from the hot glow it once was into the faint microwave radiation we detect now. The stretching of this light over cosmic time is itself a consequence of the expanding universe, and it explains why the radiation is now so cold. When the light was released, the universe was still quite hot, and the radiation was correspondingly energetic, a glow like that of a warm surface. But as space expanded over the billions of years that followed, the wavelength of the light was stretched along with it, drawn out to longer and longer wavelengths, which corresponds to lower and lower energy, and therefore lower and lower temperature. The radiation that began as a warm glow has been cooled by the expansion to just a few degrees above the coldest temperature possible, the absolute zero at which all thermal motion ceases. Today, the cosmic microwave background hovers at a temperature only slightly above that ultimate cold, a faint whisper of the heat that once filled all of space. And yet, it is everywhere, filling the entire sky, arriving from every direction, the preserved afterglow of the universe's transparent dawn. The discovery of this radiation is one of the great stories of 20th century science, and it transformed cosmology from speculation into observation. In the 1960s, two researchers working with a sensitive antenna detected a persistent hum of microwave noise that they could not eliminate no matter how carefully they cleaned and adjusted their instrument. The signal came from every direction in the sky, steady and uniform, and at first they suspected it was some flaw in their equipment. Only after checking every possibility did they realize, with the help of theorists who had predicted such radiation should exist, that they had stumbled upon the afterglow of the early universe. The predicted radiation from the hot, dense beginning had been found, exactly as the theory required. This discovery settled a long debate about the nature of the universe and established the hot, dense beginning as the correct framework, because no other picture could account for this ancient, uniform glow filling all of space. But the true richness of the cosmic microwave background lies not in its mere existence, but in the fine details of its pattern. And this is where it connects back to inflation. When the radiation was first measured, it appeared perfectly uniform, exactly the same temperature in every direction. This uniformity, as we discussed, was itself a puzzle, the horizon problem that inflation was designed to solve. But as instruments improved, cosmologists were able to measure the temperature of the radiation with ever greater precision, and they searched for tiny variations, minuscule differences in temperature from one part of the sky to another. According to inflation, such variations had to exist. The quantum fluctuations stretched by inflation should have produced tiny variations in density in the early universe, and those density variations should have left their mark on the cosmic microwave background as tiny variations in temperature. Regions that were slightly denser should appear slightly different in temperature from regions that were slightly less dense. If inflation was correct, the ancient light should not be perfectly smooth. It should carry a faint pattern, the imprint of the primordial fluctuations. For years, these variations eluded detection because they were extraordinarily small. But in the early 1990s, a satellite dedicated to measuring the cosmic microwave background finally succeeded. It detected tiny variations in the temperature of the radiation across the sky, variations of only a few parts in 100,000, precisely the scale that inflation predicted. Some regions of the sky were a minuscule fraction warmer, others a minuscule fraction cooler, and these variations traced a pattern across the entire sky. This was a landmark moment. The predicted imprint of the primordial fluctuations had been found. The seeds that inflation claimed to have planted were visible, written into the oldest light in existence, exactly where the theory said they should be. The map of these temperature variations became one of the most scrutinized images in all of science, because encoded within it was information about the earliest moments of the universe and the mechanism that shaped them. As instruments continued to improve, later satellites and ground-based observations measured this pattern with astonishing precision, and the details matched the predictions of inflation to a remarkable degree. Recall that inflation predicted the fluctuations should be nearly scale invariant, roughly the same strength across a wide range of scales, with only a slight predicted tilt. When cosmologists analyzed the pattern of temperature variations across the sky, breaking it down into its components across different scales, they found exactly this. The fluctuations were nearly the same strength across scales, with a slight tilt, precisely as inflation had predicted. This was not a vague qualitative agreement, but a quantitative match, a case where a specific numerical prediction of the theory was confirmed by careful measurement. Recall also that inflation predicted the fluctuations should follow the characteristic random statistical distribution of quantum processes. When cosmologists examined the statistical character of the variations, they found this prediction confirmed as well. The pattern was consistent with fluctuations arising from quantum processes, just as inflation claimed. The agreement between prediction and observation is what elevates inflation from an appealing idea to a serious scientific theory. It is one thing to propose a mechanism that solves several puzzles at once. It is another to have that mechanism make specific quantitative predictions about a pattern in the sky, and then to measure that pattern and find it matches. The cosmic microwave background is the testing ground where inflation confronts observation. And across a range of predictions, inflation has passed. The nearly scale invariant spectrum, the characteristic statistical distribution, the overall level of the fluctuations, all of these agree with what inflation forecasts. This is why inflation, despite the unconfirmed status of the inflated field itself, is taken so seriously by cosmologists. It has made itself vulnerable to disproof, and it has survived the confrontation with data. And yet the story is not finished, because there remains a prediction of inflation that has not yet been confirmed, a signal more elusive than the temperature variations, one that would provide even stronger evidence if it could be found. The temperature variations in the cosmic microwave background arose from variations in density, and while these are consistent with inflation, they could in principle have arisen from other mechanisms as well. There is another kind of imprint, however, that would be far more distinctive, a signal that inflation predicts, but that would be difficult to produce any other way. If inflation could be shown to have left this second imprint, it would be a far more decisive confirmation. This signal involves not variations in density but ripples in the fabric of space and time itself, and the search for it has become one of the central quests of modern cosmology. What is this more elusive signal, and why would finding it settle the question of whether inflation truly happened? The signal is a form of gravitational wave, and to understand what it is and why it would be so decisive, we need to recall a prediction of Einstein's general relativity that took a century to confirm through direct detection. General relativity describes gravity not as a force in the ordinary sense, but as a curvature of space and time, a bending of the fabric of reality by the presence of mass and energy. One consequence of this description is that violent events involving massive objects should send ripples through that fabric, disturbances that propagate outward across the universe like waves spreading across the surface of a pond. These are gravitational waves, stretches and compressions of space itself, traveling at the speed of light, carrying energy away from whatever produced them. When two massive objects, such as a pair of collapsed stars, spiral together and collide, they shake the fabric of space so violently that the resulting waves can be detected across enormous distances. And in recent years, instruments of extraordinary sensitivity have succeeded in detecting exactly such waves from distant collisions. Now consider what inflation implies about gravitational waves in the early universe. We have discussed how the quantum fluctuations of the inflated field were stretched by inflation into variations in density. But the inflated field was not the only field subject to quantum fluctuations during that era. The gravitational field itself, the very fabric of space and time, was also fluctuating, trembling with the same unavoidable quantum jitter that affects all fields. And just as the fluctuations of the inflaton were stretched by inflation and frozen into the universe, so too were the fluctuations of the gravitational field. Inflation should have stretched these quantum tremors of space and time into gravitational waves, ripples in the fabric of reality spread across cosmic scales, a background of primordial gravitational waves permeating the entire universe. These would not come from any collision or explosion. They would be the stretched quantum fluctuations of space-time itself, a relic of the inflationary era woven into the geometry of the cosmos. This prediction is what makes the search so important, because primordial gravitational waves of this kind would be very difficult to produce by any means other than inflation. The temperature variations we have already observed could conceivably arise from several different mechanisms, and so while they are consistent with inflation, they do not uniquely confirm it. But a background of gravitational waves stretched from quantum fluctuations during a phase of rapid expansion is a much more specific signature. Finding it would be strong evidence that inflation actually happened, because few, if any, alternative theories predict such a background at a detectable level. This is why cosmologists regard the detection of primordial gravitational waves as something close to a decisive test. It would be the fingerprint that inflation, and inflation almost alone, could have left. The difficulty is that these primordial gravitational waves are extraordinarily faint, far too weak to detect directly with the instruments that have found gravitational waves from colliding stars. Those instruments detect waves passing through the Earth today, produced by relatively recent and relatively nearby events. The primordial waves from inflation are spread across the entire universe and were produced in the first instant of time, and their direct effect on any detector we could build is immeasurably small. So, cosmologists have turned to an indirect method, looking not for the waves themselves, but for the mark they would have left on the cosmic microwave background, the oldest light in existence. If primordial gravitational waves were present when that light was released, they would have left a subtle imprint on it. And by searching for that imprint, we might detect the waves indirectly, reading their signature in the ancient radiation. The specific imprint they would leave involves a property of light called polarization. Light is a wave, and it can be oriented in particular directions as it travels, a property we call polarization. Sunglasses that reduce glare work by filtering light according to its polarization, blocking waves oriented in certain directions while allowing others through. The cosmic microwave background is polarized. It's light-oriented in patterns across the sky, and these patterns encode information about the conditions when the light was released. Most of the polarization arises from the density variations we have already discussed, and it forms a particular kind of pattern. But primordial gravitational waves would produce a different, more distinctive pattern of polarization, a swirling, curling arrangement that density variations alone cannot create. This special swirling pattern is the target of the search. If it can be found in the polarization of the cosmic microwave background, it would be the fingerprint of primordial gravitational waves, and therefore strong evidence for inflation. The search for this swirling polarization pattern has become one of the most intense efforts in modern cosmology, and it has also produced one of its most instructive cautionary episodes. In the year 2014, a team operating a specialized telescope announced that they had detected exactly this pattern, the swirling polarization that would signal primordial gravitational waves from inflation. The announcement caused enormous excitement, because it appeared to be the decisive confirmation that cosmologists had long sought. If correct, it would have been among the most important discoveries in the history of science, direct evidence of the inflationary era, and a window into physics at energies far beyond anything achievable in any laboratory. For a brief period, it seemed that inflation had been confirmed in the most dramatic way possible. But science demands scrutiny, and scrutiny is what followed. Other researchers examined the claim carefully, and a problem emerged. The swirling polarization pattern that the team had detected could be produced not only by primordial gravitational waves, but also by something far more mundane, by dust in our own galaxy. Tiny grains of dust scattered through the space between the stars in our galaxy can emit polarized light, and this dust can produce a swirling polarization pattern that mimics the signal from inflation. When the contribution of galactic dust was carefully accounted for, using data from other observations, it became clear that the detected signal could be explained largely or entirely by dust, without any need for primordial gravitational waves. The claimed detection did not hold up. What had appeared to be the fingerprint of inflation turned out to be, in large part, the glow of dust much closer to home. This episode, though disappointing at the time, is worth dwelling on, because it illustrates how science actually works and why we should trust its conclusions. The initial claim was made in good faith, based on real data, but it was subjected to independent scrutiny, and when that scrutiny revealed a more mundane explanation, the claim was withdrawn. The system worked as it should. A dramatic result was proposed, tested, and found wanting, and the scientific community adjusted its understanding accordingly. This is not a failure of science, but an example of its central strength: the willingness to subject even the most exciting claims to rigorous testing, and to accept the verdict of that testing even when it disappoints. The search for primordial gravitational waves continues, more careful now, with a sharper awareness of the obstacles that dust and other foregrounds present. The current situation is one of ongoing effort and genuine uncertainty. The swirling polarization pattern that would confirm inflation has not been detected, but neither has it been ruled out. It may simply be fainter than the sensitivity of current instruments can reach. Different versions of inflation predict different strengths for the primordial gravitational wave background, and some of those versions predict a signal so weak that it lies below what any current telescope can detect. If the true signal is faint, its absence in current data would not mean inflation did not happen, only that this particular fingerprint is too subtle to see with present technology. New instruments are being built and planned, telescopes of greater sensitivity dedicated to searching for this signal, and cosmologists hope that in the coming years they will either detect the swirling pattern or push the limits low enough to rule out entire classes of inflationary models. This ongoing search illustrates a broader truth about the status of inflation as a scientific theory. Inflation has passed several important tests, matching the observed pattern of temperature variations in the cosmic microwave background with impressive precision. But it has not yet passed the most decisive test, the detection of primordial gravitational waves, and until it does, a measure of uncertainty will remain. This is the honest position of the science, neither overselling the theory as proven nor dismissing it as speculation. Inflation is a well-supported framework that has made successful predictions, but its most distinctive prediction remains unconfirmed, and the effort to confirm it continues. The theory has staked out testable ground, and the tests are being carried out, one instrument at a time. There is something worth appreciating in the fact that a theory about the first fraction of a second of the universe can be tested at all. It would have been easy to imagine that the earliest moments of the cosmos were forever beyond the reach of observation, hidden behind the veil of the transparent dawn, accessible only to speculation. But the primordial gravitational wave background offers, at least in principle, a way to see even further back, past the moment the light was released, to the inflationary era itself. Because these waves were produced during inflation and would have passed through the plasma that scattered ordinary light, they carry information from before recombination, from the inflationary epoch directly. Detecting them would be like receiving a signal from the first instant of time, a message stretched across the entire history of the universe and arriving faintly in our instruments today. That such a message might be readable at all is a remarkable prospect, and it drives the continuing search. But even as cosmologists pursue this signal, the theory of inflation has led some of its own architects to a conclusion that reaches far beyond any single measurement. A conclusion that emerges from the mathematics of inflation itself, and that reshapes our conception of what the universe might be. For when physicists examined closely the question of how inflation ends, they discovered something unexpected and strange. In many versions of the theory, inflation does not end everywhere at once. It ends in some regions while continuing in others, and the regions where it continues expand so rapidly that they come to dominate, spawning ever more regions in an endless cascade. This possibility carries implications so sweeping that they challenge our most basic assumptions about the nature of reality itself. What if inflation, once begun, never entirely stops? This idea is called eternal inflation, and it emerges not from wild speculation but from taking the mathematics of inflation seriously and following it to its logical conclusion. To understand how inflation could become eternal, we must return to the quantum fluctuations of the inflaton field, the same fluctuations that seeded cosmic structure. We have discussed how these fluctuations nudged the field slightly ahead or slightly behind in its roll down the landscape of energy. In most places, and in most versions of the theory, these nudges are small compared to the overall progress of the field, and the field rolls steadily downhill, eventually reaching the valley floor where inflation ends. But consider what happens if the quantum fluctuations are large enough, or the landscape flat enough, that in some regions the fluctuations nudge the field backward, uphill, faster than the steady rolling carries it downhill. In such regions, the field does not progress toward the end of inflation. Instead, the quantum jitter keeps kicking it back up the slope, keeping it high on the energy landscape, and so inflation continues in those regions rather than ending. And here, the exponential nature of inflation becomes decisive. The regions where inflation continues are expanding at a colossal rate, doubling and redoubling, while the regions where inflation has ended are not. This means that the regions still inflating rapidly come to occupy vastly more volume than the regions where inflation has stopped. Even if inflation ends in most places, the rare regions where it continues expand so enormously that they dominate the total volume. And within those still inflating regions, new fluctuations continually push some subregions to keep inflating while others stop. The process never completes. Inflation ends here and there in isolated pockets, but the inflating background between those pockets keeps expanding faster than the pockets can consume it, generating new space endlessly. The picture that emerges is one of an inflating expanse that never entirely ceases, within which pockets of ended inflation continually form, like bubbles appearing in an endlessly expanding sea. Each bubble is a region where inflation has stopped and the energy of the inflaton field has been released, giving rise to a hot, expanding, matter-filled universe of the kind we inhabit. Our entire observable universe in this picture would be the interior of one such bubble, one region where inflation ended and gave birth to a cosmos. But beyond our bubble, separated from us by regions still inflating, there would be other bubbles, other universes, each one a place where inflation ended and a new cosmos began. And because the inflating background never stops, new bubbles form endlessly, an unlimited number of them, each a universe unto itself. This is the multiverse, the collection of all these bubble universes embedded in the eternally inflating expanse. We must be careful and honest about the status of this idea, because it occupies a different epistemic position than the core theory of inflation. The prediction that inflation seeded cosmic structure through quantum fluctuations is testable, and it has been tested, matching observations of the cosmic microwave background. Eternal inflation and the multiverse are different. They emerge as a consequence of certain versions of inflation, following from the mathematics when it is extended in a particular way, but they make claims about regions of reality that lie forever beyond our observation. The other bubble universes, if they exist, are separated from us by regions still inflating, expanding faster than light could cross them, and so we can never see them, never visit them, never receive any signal from them. They are, by the very nature of the theory, beyond the reach of direct observation. This places the multiverse in an unusual scientific position, a possible consequence of a testable theory that is itself not directly testable. Some physicists embrace this consequence, arguing that if our best theory of the early universe implies a multiverse, then we should take that implication seriously, even if we cannot observe the other universes directly. They point out that theories often predict things we cannot directly observe, and that we accept those predictions when they follow from a well-supported framework. If inflation is correct, and if the versions of inflation that lead to eternal inflation are the right ones, then the multiverse may simply be a feature of reality, whether or not we can see it. Other physicists are more skeptical. worried that a theory predicting unobservable universes strays beyond the boundaries of testable science into a realm where claims cannot be checked against evidence. This is a genuine and unresolved debate within cosmology, a disagreement not about the mathematics, which is largely agreed upon, but about what the mathematics means and how seriously to take its more extravagant implications. The multiverse idea connects to another deep question, one that has troubled physicists for decades, and that the multiverse offers a controversial way of addressing. When physicists examine the fundamental constants of nature, the numbers that determine the strengths of the forces and the masses of the particles, they find that many of these numbers appear to be finely tuned in a way that permits the existence of complex structures like stars, planets, and life. If certain of these constants were even slightly different, the universe would be a barren place, with no stars to forge the elements, no chemistry to build complex molecules, no possibility of anything resembling life. This apparent fine-tuning has long puzzled physicists who wonder why the constants should have values so favorable to the emergence of complexity. The multiverse offers one possible answer to this puzzle, though a contested one. If there are countless bubble universes, and if the fundamental constants vary from one bubble to another, taking different values in different universes, then the vast majority of bubbles might be barren, hostile to complexity and life. But a small fraction, by chance, would have constants that permit stars and chemistry and life. And of course, we find ourselves in one of those rare, hospitable bubbles, because we could not exist in any of the barren ones. On this reasoning, the apparent fine-tuning of our universe is not a mystery requiring some deep explanation. It is simply a selection effect. Among the countless universes with varying constants, only the rare hospitable ones could give rise to observers, and so any observer, by necessity, finds themselves in a hospitable universe. The fine-tuning we observe is explained not by design or by deep necessity, but by the fact that we could only exist where the conditions allow it. This line of reasoning is called the anthropic argument, and it is among the most controversial ideas in modern physics. Some find it a satisfying resolution to the fine-tuning puzzle, a way of explaining the favorable constants without invoking anything beyond the natural variation of a multiverse. Others find it deeply unsatisfying, arguing that it explains too little, that it amounts to saying the constants are what they are, because otherwise we would not be here to ask, which some regard as an evasion rather than an explanation. The debate touches on fundamental questions about what counts as a scientific explanation, and whether a theory that appeals to unobservable universes and selection effects can be considered proper science at all. There is no consensus, and the disagreement runs deep, reflecting genuine philosophical differences about the goals and limits of physical theory. It is worth stepping back to appreciate how far this chain of reasoning has carried us from its starting point. We began with concrete puzzles about the observable universe, the uniformity of its temperature, the flatness of its geometry, the absence of certain particles. These were empirical problems, grounded in observation, and inflation was proposed to solve them. But following the logic of inflation to its conclusions has led us to eternal inflation, to a multiverse of bubble universes, to anthropic reasoning about fine-tuning, ideas that lie at the very edge of what science can address, and perhaps beyond that edge. This progression illustrates something important about how theoretical physics operates. A theory proposed to solve specific problems can, when its implications are pursued rigorously, lead to conclusions far more sweeping than anyone intended, conclusions that reshape our conception of reality itself. Whether these sweeping conclusions are correct is a question that may never be settled, at least not by direct observation. The multiverse, if it exists, remains hidden behind the veil of inflation, its other universes forever beyond our sight. This does not necessarily mean the idea is wrong, but it does mean that our confidence in it must rest on different grounds than our confidence in the testable predictions of inflation. We accept that inflation seeded cosmic structure because we can check that prediction against the cosmic microwave background and find it confirmed. We cannot check the existence of other bubble universes in the same way, and so the multiverse remains, for now, a fascinating possibility rather than an established fact, an implication of our theories that we can reason about but not directly verify. This distinction between what we can test and what we can only infer brings us to a necessary reckoning with the limits of the inflationary theory itself. For all its successes, inflation is not without its problems and its critics. It has matched important observations, but it also carries unresolved difficulties, gaps in its foundations that honest scientists acknowledge and continue to grapple with. And there are alternative theories, competing accounts of the early universe that attempt to explain the same observations through different mechanisms. To understand the true status of inflation, we must confront these difficulties and consider these alternatives, examining not only what the theory explains, but also what it leaves unexplained and where it might be wrong. What are the weaknesses in the inflationary picture, and what would it take to know whether inflation truly happened? The first and most fundamental difficulty concerns the beginning of inflation itself, the question of how the whole process got started. Inflation explains a great deal about what happens once the inflaton field is poised high on its energy landscape, ready to roll slowly across the plateau and drive the exponential expansion. But it does not explain how the field came to be in that special starting position in the first place. For inflation to begin, a region of the early universe had to contain the inflaton field sitting high on its plateau with the right energy, over a region large enough and smooth enough for inflation to take hold. And here a troubling circularity appears. Inflation was proposed in part to explain why the universe is smooth and uniform. But for inflation to begin, it seems to require a patch that is already somewhat smooth and uniform to start with. If inflation needs a smooth starting patch to explain the smoothness of the universe, then it has not fully solved the problem it was meant to solve. It has pushed the requirement for smoothness back to the initial conditions of inflation itself. This is a genuine and much discussed difficulty, sometimes called the initial conditions problem for inflation. Defenders of the theory argue that the patch required to start inflation need not be as smooth or as large as the universe we observe, that inflation can begin in a relatively modest region and then stretch it to cosmic proportions, so that the smoothness required at the start is far less demanding than the smoothness inflation produces. On this view, inflation still accomplishes a great deal, taking a small and only modestly smooth patch and amplifying it into a vast and highly uniform universe. Critics respond that even this more modest requirement is not obviously satisfied, that we have no clear account of why any patch of the early universe should have had even the modest smoothness that inflation requires to begin. The debate remains unresolved, and it touches on the deepest questions about the initial state of the universe, questions that reach back toward the Planck era and the missing theory of quantum gravity. A second difficulty concerns the nature of the inflaton field itself. We have spoken of this field as though it were a definite entity, but the truth is that we do not know what it is. In the standard framework of particle physics, which describes all the known particles and forces with remarkable precision, there is no field that naturally plays the role of the inflaton. The inflaton is an addition, a field proposed specifically to drive inflation, not something that emerges necessarily from the established physics of particles. This means that inflation requires us to postulate a new field, with a carefully shaped energy landscape that has never been observed and that does not follow from any independently confirmed theory. Some physicists find this troubling, arguing that a theory which requires an entirely new and unobserved field, with properties tuned to produce the desired outcome, is less compelling than a theory that follows from established physics. The inflaton might exist, but its existence is an assumption, and the shape of its landscape is chosen to fit the observations rather than derived from first principles. This connects to a broader concern about the flexibility of inflation as a theory. Because the shape of the inflaton's energy landscape is not known, and because different shapes produce different predictions, inflation is not a single theory, but a large family of related models, each with a different landscape and different detailed predictions. Some critics argue that this flexibility is a weakness, that a theory with so many adjustable possibilities can be made to fit almost any observation, and that a theory able to accommodate any result is not making genuine predictions. If the swirling polarization pattern is found, there are versions of inflation that predict it. If it is not found, there are versions of inflation that predict its absence. A theory that can accommodate both outcomes, the critics argue, is not being tested in any meaningful sense. Defenders respond that this criticism is overstated, that while inflation is a family of models, the family as a whole makes definite predictions that have been confirmed, such as the nearly scale invariant spectrum and the flat geometry, and that individual models within the family make specific predictions that can be tested and ruled out. The disagreement reflects a genuine tension in how to evaluate a theory that comes in many variants. There is a further and quite subtle difficulty, one that emerges from the eternal inflation we discussed earlier, and that troubles even some of inflation's strongest supporters. If eternal inflation produces an unlimited number of bubble universes, then in trying to make predictions about what we should observe, we run into a problem of counting. To predict what a typical observer should see, we would need to count the observers in different kinds of bubbles and determine what most of them experience. But when there are infinitely many bubbles of infinitely many kinds, this counting becomes mathematically ill-defined. There is no unique way to compare infinite quantities, no agreed method for determining what fraction of observers see one thing rather than another. This is called the measure problem, and it strikes at the ability of eternal inflation to make predictions at all. If we cannot say what a typical observer should see because the counting is undefined, then the theory loses some of its predictive power in exactly the regime where its most dramatic consequences appear. This is a serious technical problem, acknowledged by cosmologists working in the field, and it remains without a satisfactory solution. Given these difficulties, it is natural to ask whether there are alternatives, other theories that might explain the same observations without invoking inflation. And there are. Cosmologists have proposed several competing frameworks, each attempting to account for the uniformity, flatness, and structure of the universe through mechanisms other than a burst of exponential expansion. One family of alternatives proposes that instead of a rapid expansion, the early universe underwent a slow contraction before the expansion we observe, a phase in which the universe shrank rather than grew, smoothing itself in the process before bouncing into the expanding phase. These are sometimes called bouncing cosmologies, because they replace the beginning with a transition from a previous contracting phase, a bounce from contraction to expansion. In some versions, the smoothing and flattening that inflation attributes to rapid expansion is instead accomplished during the slow contraction, producing a universe with properties similar to what we observe, but through a very different history. These alternative theories are worth taking seriously, not because they are clearly superior to inflation, but because their existence reminds us that inflation is not the only conceivable explanation for the observations. A single theory that fits the data is more convincing when it has been compared against genuine competitors and found to fit better, and less convincing when it stands alone, untested against alternatives. The alternatives to inflation face their own difficulties, and none has achieved the observational success or the broad acceptance that inflation enjoys. But they play an important role in the scientific process, providing a standard against which inflation can be measured and pointing toward observations that might distinguish between the competing pictures. If some future measurement could tell us whether the early universe expanded rapidly or contracted slowly, it would help settle the question of which framework is correct, and the existence of alternatives sharpens our sense of what such a measurement would need to show. The comparison between inflation and its alternatives often comes down to the primordial gravitational waves we discussed earlier. Inflation, in many of its versions, predicts a background of these waves, the stretched quantum fluctuations of space-time, potentially detectable through the swirling polarization pattern in the cosmic microwave background. Many of the bouncing alternatives predict a much weaker signal, or a different pattern, because they do not involve the rapid expansion that stretches the gravitational fluctuations to cosmic scales. This means that the search for primordial gravitational waves is not only a test of inflation in isolation, but also a way of distinguishing between inflation and its competitors. If the swirling pattern is found at a strength consistent with inflation, it would favor inflation over the bouncing alternatives. If it is found to be absent below a level that most inflationary models require, it would favor the alternatives, or at least the versions of inflation that predict a weak signal. The observational effort, in other words, has the potential to adjudicate between competing theories, not merely to confirm or deny a single one. This is the honest and somewhat unsettled state of the science. Inflation is the leading theory of the early universe, supported by important observational successes, but it carries unresolved difficulties, requires an unobserved field, comes in many variants, and faces the measure problem in its eternal form. It has serious competitors that, while less successful so far, remain viable and offer different accounts of the same observations. The most decisive test, the detection of primordial gravitational waves, has not yet been carried out, and until it is, a genuine uncertainty will persist about whether inflation truly describes the first moments of the universe. This uncertainty is not a scandal or a weakness. It is the ordinary condition of science at the frontier, where the questions are hardest and the evidence is most difficult to obtain. Inflation has earned its place as the leading theory, but it has not yet earned the status of established fact, and honest cosmologists hold it with appropriate tentativeness. What makes this situation scientifically healthy rather than troubling is that the questions are answerable in principle. These are not matters of pure speculation, beyond any possible resolution. The detection or exclusion of primordial gravitational waves, the improved measurement of the cosmic microwave background, the search for signatures that might distinguish inflation from bouncing cosmologies, all of these are observational programs actively being pursued, and any of them could shift the balance of evidence in the coming years. The theory has made itself vulnerable to disproof, and the tests are being carried out. This is what separates inflation, for all its unresolved difficulties, from mere philosophical speculation about the origin of things. It connects to observation, and observation can, in time, render a verdict. And so we arrive at a moment of reflection, having traced the theory of inflation from the puzzles that motivated it, through the mechanism it proposes, to the evidence that supports it and the difficulties that trouble it. We have seen how a single idea, born in the study of particle physics, came to explain the uniformity, flatness, and structure of the universe, and how following that idea to its conclusions led to visions of a multiverse at the very edge of what science can address. We have seen what inflation explains and what it leaves unexplained, what it predicts and what remains to be tested. What then does all of this tell us about our origins, about the first moment of the universe and our place within the vast structure that emerged from it? And why does the search for that first moment continue to occupy some of the finest scientific minds, despite all the difficulties that stand in the way? The answer begins with an appreciation of what inflation, if correct, tells us about the connection between the smallest and the largest scales of reality, a connection that stands as one of the most remarkable ideas in all of science. We have followed the claim that the great structures of the cosmos, the galaxies and clusters and filaments that span the observable universe, grew from quantum fluctuations, from the irreducible jitter of a field at scales far smaller than any particle. If this is true, then the universe we inhabit is, in the most literal sense, a magnified quantum fluctuation, an enlargement of the tiny random tremors that inflation stretched across space. The arrangement of galaxies in the sky, the distribution of matter across billions of light years, the particular pattern of structure that we observe when we map the cosmos, all of it traces back to quantum events in the first fraction of a second. The largest things in existence are the grown-up descendants of the smallest, and the bridge between them is inflation. This connection carries a certain intellectual weight that is worth pausing to absorb. In ordinary experience, the quantum world and the cosmic world seem utterly separate, governed by different rules, operating at scales so different that they never seem to touch. The quantum world is the realm of the exceedingly small, of particles and probabilities and uncertainty. The cosmic world is the realm of the exceedingly large, of galaxies and gravity and the sweep of billions of years. Inflation proposes that these two realms are joined at the origin, that the cosmic grew directly from the quantum, that the same uncertainty principle which governs the behavior of particles also, through inflation, determined the arrangement of the galaxies. When you look at a map of the universe and trace the great filaments of galaxies stretching across the sky, you are looking at quantum mechanics written large, the fingerprint of the subatomic imprinted on the grandest structures that exist. There is a further consequence that follows from this, one that touches on our own existence. If the structure of the universe grew from quantum fluctuations, then the particular arrangement of matter that led to our galaxy, our solar system, and ultimately ourselves, traces back to a specific set of quantum tremors in the early universe. Had those fluctuations been slightly different, the pattern of structure would have been different. Galaxies would have formed in different places, and the particular conditions that gave rise to our existence might never have occurred. In this sense, our presence in the universe is connected, through an unbroken chain of cause and effect, to the quantum jitter of a field in the first instant of time. This is not mysticism or poetry, but a consequence of the physics, if inflation is correct. The origin of everything we are, everything we can see, lies in those first magnified fluctuations, and the chain of causation runs directly from them to us. We should hold this idea with appropriate care, remembering the uncertainties we have discussed. Inflation is the leading theory, supported by real evidence, but not yet confirmed by its most decisive test. The connection between quantum fluctuations and cosmic structure is a claim of the theory, well supported by the match between prediction and observation in the cosmic microwave background, but resting ultimately on a framework that has not been established beyond doubt. If inflation is correct, then the account of our origins in magnified quantum fluctuations follows. If inflation turns out to be wrong, replaced by some alternative, then the story of our origins would be told differently, through whatever mechanism the correct theory provides. The picture is compelling, but it is provisional, held with the tentativeness that honest science requires. What is not provisional is the remarkable fact that we can investigate these questions at all. Step back and consider what it means that beings on a small planet, orbiting an ordinary star in one galaxy among countless others, can reason their way back to the first fraction of a second of the universe, can propose mechanisms for what happened then, and can test those mechanisms against observations of the oldest light in existence. The universe has been expanding and evolving for billions of years, cooling from its hot, dense beginning through the long ages that produced stars and galaxies and eventually the conditions for life. And now, at this late stage, a part of that universe has become capable of understanding its own origins, of tracing the history back toward the beginning, and asking how it all started. This capacity for self-understanding, this ability of the cosmos to comprehend itself through the minds of its inhabitants, is among the most extraordinary features of reality, and it is what makes the investigation of the first moment possible. The tools of that investigation are worth recalling because they represent a triumph of ingenuity in the face of enormous obstacles. We cannot travel back in time to observe the early universe directly. We cannot recreate the conditions of inflation in any laboratory, because the energies involved are far beyond anything we can produce, and yet we are not without evidence. The cosmic microwave background carries a picture of the universe as it was when it became transparent, and encoded in its faint variations is information about the primordial fluctuations that inflation predicts. By measuring that ancient light with ever greater precision, cosmologists read the record of the early universe, testing their theories against the imprint left in the oldest light in existence. The search for primordial gravitational waves, if it succeeds, would push the record back even further, to the inflationary era itself. These are indirect methods, requiring great ingenuity and care, but they connect our theories to observation, and observation is what separates science from speculation. The continuing search for the first moment is driven, in part, by the questions that inflation has not yet answered. We do not know what the inflaton field is, or whether it exists at all. We do not know the shape of its energy landscape. Which version of inflation, if any, describes what actually happened? We do not know whether inflation was eternal, whether the multiverse is real, whether the other bubble universes exist beyond our sight. We do not know whether inflation happened at all, or whether some alternative theory, some bouncing cosmology or as yet unimagined mechanism provides the correct account of the early universe. These open questions are not signs of failure, but invitations to further inquiry, problems that drive the ongoing effort to understand our origins. Each unanswered question points toward observations that might answer it, measurements that might distinguish between the possibilities, and the pursuit of those measurements is what keeps the field alive and moving forward. There is a particular question that deserves emphasis, because it lies at the very foundation and remains beyond our current reach. Inflation, even if fully confirmed, does not explain the ultimate beginning, the very first instant, the Planck era where our theories break down. Inflation describes what happened after the universe was already in existence, already governed by the physics of fields and expansion. It does not explain how the universe came to exist in the first place, or what determined the initial conditions from which inflation began. To answer those deepest questions, we would need a theory of quantum gravity, a unification of the physics of the large and the small that could describe the earliest instant before inflation, when the entire universe was smaller than an atom, and the familiar rules had not yet taken hold. Such a theory does not yet exist in finished form, and until it does, the ultimate beginning remains beyond our understanding, a frontier that inflation approaches but does not cross. This is perhaps the most honest note on which to reflect. For all that we have learned, for all the successive inflation in explaining the uniformity and flatness and structure of the universe, the deepest question of all, the question of the ultimate origin, remains unanswered. We have traced the history back to the first fraction of a second, and inflation offers a compelling account of what happened then. But behind inflation lies the Planck era. And behind the Planck era lies the question of why there is a universe at all. Questions that our current physics cannot address. The search for the first moment has carried us remarkably far, but it has not carried us all the way. And the final steps, if they can be taken at all, await a theory we do not yet possess. And yet the trajectory of the science gives reason for a measured optimism. A century ago, the expansion of the universe had not yet been discovered, and the idea that we might understand the first moments of the cosmos would have seemed beyond reach. Since then, we have discovered the expansion, detected the oldest light in existence, measured its faint variations, and developed a theory that connects those variations to quantum fluctuations in the first instant. Each of these was once thought difficult or impossible, and each was achieved through patient observation and careful reasoning. There is no reason to assume that the questions still open today are permanently beyond our reach. The primordial gravitational waves may yet be detected. The nature of the inflaton may yet be understood. A theory of quantum gravity may yet be developed, opening a window onto the ultimate beginning. The history of cosmology is a history of questions once thought unanswerable, yielding, in time, to observation and thought. So the search continues, not out of idle curiosity, but out of the deep human impulse to understand where we came from and how the universe that contains us began. Inflation stands as our best current attempt to describe the first moments, a theory of remarkable reach and genuine success, held with appropriate tentativeness because its most decisive test remains to be carried out. Whether it is ultimately confirmed or replaced, it has transformed our understanding of the early universe, connecting the quantum and the cosmic, explaining puzzles that once seemed intractable, and pointing toward observations that continue to drive the field forward. The first moments of the universe, once thought forever hidden, have become a subject of serious scientific investigation, and the effort to understand them, to read the record left in the oldest light and to trace the history back toward the beginning, remains one of the great ongoing endeavors of the human mind. The universe began in a way we are only beginning to comprehend, and the pursuit of that comprehension, patient and rigorous and open to wonder, is far from over.